welcome to this course on algebraic geometry and commutative algebra. And now I go back to, we have little bit commutative algebra background. So, I will go back to the first lecture where we have defined affine algebraic sets. So, let us recall what we have defined. So, K was our base field and L over K a field extension with L algebraically close. This is our setup, and just to recall a word about algebraically close, that means every non-constant polynomial with coefficients in L in one variable has a 0 in L. That is a definition of an algebraically closed field. Alright, and typical examples are the following three cases. So, where we apply these to the following three cases. Number 1, K equal to R and L equal to C. This is C, the algebraic closure of R, that we assume that you know that C is an algebraically closed field and C is an algebraic extension of R. Therefore, C is an algebraic closure of R, and in fact it has a degree 2. And when we apply this special case, what we will get is classical algebraic geometry. This is said, this is the very old subject and it was lot of applications in different fields, in different real fields. Alright, so second one is K equal to Q. Q is the field of rational numbers, and either L you can take C or L you can take Q bar. Q bar is the algebraic closure of Q inside C. So, that means what? That means this Q bar is set of all those complex numbers Z such that this Z is a 0 of a monic polynomial. So, such that f of Z is 0 for some non-zero polynomial f with coefficients in the rational numbers, and yeah. So, this is a monic. This is also called this field of algebraic numbers. This is also known as the field of algebraic numbers. So, this way, if you take this K equal to Q and L equal to Q bar, this is a very famous now upcoming or very front line research area in algebraic geometry, which is also known as arithmetic geometry. So, because it arose from the arithmetic is the numbers, so the numbers which arose from natural numbers, integers and the rational numbers. There is no limiting process here. Alright, the last one is, this is where the C part is very useful for engineering purposes. That is, K is F, finite field, and L is the algebraic closure of F. bar, the algebraic closure. Of F. We have assumed that every field has an algebraic closure. So, these are the it depends on what you want to do, it depends on the field, base field as well as the upper field that you choose. And what did we define last time? We have defined, so let me write a definition here. This is what we have defined last time. Definition. We have finitely many polynomials f1 to fm with coefficients in the base field in n variables, and the affine algebraic set, the affine K algebraic set defined by these polynomials f1 to fm is V. Now, I have put a suffix L here of f1 to fm. These are the common solutions or common zeros of the polynomials f1 to fm, and the zeros has coordinates in L. So, this means these are all tuples A1 to AN in L power n such that Fj at A is 0 for all j from 1 to m. This is what we have defined affine K algebraic set. So, this is a subset of L power n. This is a subset of that finite dimensional vector space over L power n, but we are going to put more structure on that vector space actually. So, that will come final, but we are our objects of study these common solution sets, and we have noticed last time that this VL of f1 to fm, this is intersection of all this VL of Fj. They are common zeros of this thing. So, sometimes it is enough to study these particular ones and look at their intersection. This is one thing we have noticed. Another thing we have noticed that this VL of f1 to fm does not depend on these polynomial, but it depends only on the ideal generated by these polynomials in now in a polynomial ring in k x1 to xn. So, this is same thing as VL ideal generated by f1 to fm. So, where this f1 to fm is the ideal generated by f1 to fm in the polynomial ring over k in these n variables, and we have described this ideal in like this is precisely the linear combination of these polynomials with coefficients in this polynomial ring. So, this is precisely G1 f1 plus G m fm, where these G1 to Gm they vary in the polynomials over k. This is precisely this ideal, and it is clear actually from this description that if Fi's vanish at some point in Ln, then this combination also vanishes, because we know that how do you evaluate the product and how do you evaluate the sum, because evaluation or substitution map is an algebra homomorphism. So, therefore, if Fi's vanish, this combination vanishes. Conversely, if combination vanishes, obviously these Fi's are part here, then therefore vanishing depends only on the ideal. So, we might as well have defined VL of any ideal. So, we therefore define more generally VL of any ideal A, where A is an ideal in the polynomial ring over K. But then here one might ask whether ideals are generated by finitely many polynomials, and the answer is yes, and that we will prove short while, where that is known as Hilbert's basis theorem. So, I will just quote it here and go on for some time, and then when we come back to algebraic digression, we will prove Hilbert basis theorem. So, Hilbert basis theorem says every ideal A in the polynomial ring over a field K is finitely generated. So, we will assume this today and prove it in the next time when we switch to algebra. And what is VL of A formally? This is by definition then all those points A equal to A1 to AN in L power n such that f of A is 0 for every f in the ideal A. So, this VLA is a subset of L power n. Alright, now one more observation I want to make. This is called an affine. So, I will write on the next page. VLA is called the affine K algebraic set defined by an ideal A inside the polynomial ring Kx1 to Xn. Now, one might, I just want to make one comment here. Why do I keep writing this adjective affine? There is also projective, but we may not do in this course, but that is also very interesting, because nowadays projective geometry is used in mobile applications. So, that has again revived interest from the engineering side. But unfortunately, our courses on linear algebra and algebra are not taught in the university setup. So, one should take up such courses. Alright. So, this is affine algebraic set. Now, one more observation. So, observation, and then we will this set, this algebraic set VLA depends only on the so called radical ideal, radical of the ideal A and not on A. So, before I go on, before I define radical formally, I want to give one example. So, example, so let us take k equal to R, or maybe k equal to C I want to take. K equal to C and L is also equal to C. Now, you see, first of all, drawing a picture is little bit tricky, because I want to take n equal to 2. So, therefore, what is L power 2? This is C power 2. So, this is C cross C. So, if one cannot draw this picture on the board, because this is a 4-dimensional real space. So, what convention we do it, we when I draw a picture of this, I do this as C and this is C. This is x axis for C and y axis is also for C. So, our complex variables, and suppose now I take ideal A. So, where now what is the base field is also C and upper field is also L. So, now what is the number of variables? So, we are considering the polynomial ring over C in 2 variables. Let me write it Z and W, the variables, just to. So, this is a Z axis and this is a W axis. And the points here are complex numbers, and points in this C2 are precisely the pair of complex numbers. And now I take, we need an ideal. So, I take an ideal A, which is generated by Z. So, this is a principal ideal in this ring generated by Z. So, now what is V C of this ideal? So, let me indicate that V C, that means Z is 0. So, that means this is W axis. The W axis is precisely this. This is precisely V C of Z. Z is 0. So, it is the W axis. Now, suppose I would have taken ideal B is ideal generated by Z square. Then what will it be? Picture says Z square equal to 0. So, V C of B, all zeros of this Z square. But if Z square is 0, then Z is also 0, because we are in a complex number field. So, therefore, if I want to draw the picture, it will be the same W, but it should be more thicker, because it comes twice. But as a set they are equal. So, as a set there is no difference. But so this equality means as a set, but ideals are not equal, but A is not B. So, you see, when we go from algebra to geometry, this information is lost, that the points are twice, or we have to make a special efforts to say that we are counting these points twice, and that effort is seen in algebra but not in geometry. So sometimes geometry loses information, the precise information. Okay. So this we have to take care afterwards when we become more serious geometry, and how do you come back to algebra, that we have to make more and more clearer. And there is nothing special about z square. If you would have taken in fact z power m, if I would have taken the ideal C equal to ideal generated by z power m, then also this affine algebraic set defined by z power m is same as this C. And then it has to go more thicker, it has to go, this is very thick, this M. So this example shows that algebra gives more precise information. That is one of the reasons why one has to study more commutative algebra, and that is what we will do in this course. All right. So, and how do you solve? How do you remedy? I want to make some solution to this so that this does not arise right now. So, then I not modify, I just define now radical ideal, this one, this phrase radical, it depends only on the radical. So, therefore, this ideal A, this B is also A square, B is also A square ideal, square of this ideal, which is A times A, that we defined operations on the ideal. This C is nothing but A power m. All right. So, I want to define therefore first what is radical of an ideal. Now, see, this becomes algebra. So, let us go and define. So, definition. Now, this definition makes sense in any ring. So, I will not only in the polynomial ring but arbitrary ring. So, let A be an arbitrary commutative ring of course always with identity, we do not consider other rings, and also an ideal A in A, Gothic A in the ring A. Also we have notation for the set of ideals. So, let us use it, A belonging to the I of A, that means it is an ideal in A, is called a radical ideal if. So, first I will define what is when I say radical. So, this root of A, this is what is this by definition. This is by definition all those f in A, all those elements f in A such that power of this f power r belong to the ideal A. Then you call it a radical ideal. All right. So, first of all one checks that this is an ideal in A, ideal in A, and also it is clear and clearly this radical is a bigger ideal. A is contained in the root of A. One calls it also root of the ideal A or a radical of A. So, when do you call it a radical ideal? If A equal to root of A. Now, what does this mean? Let us spell out this. This means, see, this inclusion is always true. So, the other inclusion. So, we are interested in when this inclusion happens. That means, if f belongs here, then it should belong here. So, that means if for, so note that A equal to root of A, if and only if for every f in A, if f power r belongs to A, then already f belongs to A. This is for some r, for some natural number r, for some r bigger equal to 0, then A should already belong. So, because this side, what is this f belongs here means the power of f belongs to the ideal, then it should already belong to A. So, that means this what I wrote if and only if. Now, some examples of radical ideals. See, always whenever we have a concept, we should tell when is what are the examples of that kind and not of that kind. So, some examples. One, every prime ideal is a radical ideal. This is obvious, because if power of an element belong to the prime ideal, then one of them means the element should belong to the ideal. That means it's a, that is follows from the prime ideal, definition of a prime ideal. So, in particular, every maximal ideal is a radical ideal. So, in particular, a special case, if I take A equal to k x1 to xn, polynomial ring, and K is a field, this is the case we are interested always. Then this ideal MA, which is ideal generated by x1 minus a1 xn minus an, this is where A equal to a1 a to an in k power n, this ideal is a radical ideal. Because we saw these ideals are maximal ideals, and therefore they are prime ideal, therefore they are radical ideals. All right. Now at least one example of a non-radical. So, some more examples. From these examples we construct more examples. That is always the intersection of radical is always radical. Intersection of radical ideals is again a radical ideal. Finite intersection definitely. All right. Product is not a radical ideal, for example. For example, if I multiply A by A, that is A square, and A square, there is no reason that A square equal to A. Like in earlier our example, ideal generated by Z square is not a radical ideal. All right. So, we have examples. Now, let us go on. So, this is radical ideal. So, what did we do in this? So, let us see what we have achieved. So, that means what? Let us get back to our original setup. We are defining now a map from the set of radical ideals. So, radical, I want to create a notation. So, R for radical ideals and I of k x1 to xn. This is the set of all radical ideals in the polynomial ring with coefficients in capital K. And we saw this is non-empty set. In fact, this will contain all prime ideals. It will contain spec of kx1 to xn. So there are many elements. In fact, so in particular it will also contain SPM, also it will contain a K spectrum. Alright, so and then we have defined a map. So we have defined a map from where to where? VL, this is a map from R I kx1 to xn, set of all radical ideals from here to where? To affine K algebraic sets. And these are where? This is a subset of, so maybe I should put a bracket here. This is a subset of, so this do I have a name for this? Yes, let us give a name for this also. AFF ALG suffix k of L power n. And this is a subset of whom? Each one of them, this is a subset of power set of L power n. So we have defined this map, namely any ideal A goes to VL of A. So this is by definition power set of L power n. It is a huge set. So first of all this map I want to study more intimately, because if you notice this side is commutative algebra, studying radical ideals, maximal ideal, prime ideal, this is this algebraic set, and this side are the geometric objects where I can draw pictures. Also I am going to define a topology. So I can talk about open sets, closed sets, and so on. So this will give first, so if I could prove, when can I prove that this map is bijective? That is where I will concentrate. I am looking for some assumptions so that this will tell us this map is bijective. This is what we are looking for. This is what we are looking for. So why? Because if you have bijective, then we can go from here to geometry and we can come back to algebra, and that will become what is known as algebraic geometry. And one without the other will be incomplete, in the sense you cannot really study geometry without algebra, and algebra, if you study very algebra without any geometry, it becomes a dry algebra, non-interesting. So the motivation to study algebra will come from geometry, and algebra will give you very technical support for geometry to formulate statements correctly and to prove them correctly and so on. So our aim is to come to a situation where it is bijective, that is the best possibility. But obviously in life that best possibility does not happen. So at least we should know when it is injective, surjective and so on. So this is what I will carry it on in the next couple of lectures, and after the break, first of all I want to give some examples. And so for example, obvious examples are what? First of all, not every affine algebra, not every subset is an affine algebraic K set. let me give that example right away. So, let us go to the next page. So, let us see some example. Example, let us take K to be R and L to be C. This is the classical situation. And now what we are looking? We are looking at the power set of, and I am taking n equal to 2. Or even n equal to 1, let us take. Even n equal to 1 we can take. N equal to 1. So that means what is our map now? VL. VL is a map from radical ideals of the polynomial ring over R in one variable Rx to power set of L, which is power set of C. And here are the affine A double F, ALG, R sets. That means this is a subset here. This one, I don't have to write the bracket now here because that is what we have denoted. So, alright, now let us see whether this map is surjective. So, what does that mean? Surjectivity means given any element in the power set, whether is it coming from some ideal here. So, for example, what is C? I will denote C now as a real plane, and any subset here will be some subset here I can draw. Okay. Now, let us for example take this set, this is the imaginary axis. I should draw a better picture. This is a plane, and let us take this one, this axis. So, remember we have only one variable and a real polynomial, and first of all remember that what are the ideals? We know the description of ideals in a polynomial ring in one variable over a field. So, what are all ideals in Rx? We know this. All ideals in Rx are precisely the principal ideal generated by a polynomial. This statement follows from the fact that Rx is a Euclidean domain, because there is a Euclidean algorithm. You can divide arbitrary polynomial by monic polynomial and get remainder and so on. So, every ideal, so the set of ideals is precisely ideal generated by a single polynomial f, where f is arbitrary polynomial in Rx, and if you want this to be a unique generator, then one assumes that f is monic. These are all ideals. And how do you write all radical ideals? All radical ideals are simply, now we have to look at the prime decomposition of f and then remove those multiplicities. That means what? You write f as product of pi 1 power r1 pi t power rt, where these pi 1 to pi t are monic irreducible polynomials in Rx, and these r1 to rt are positive natural numbers. Every polynomial you can write uniquely like this. These pi 1 to pi t are called the prime factors of f, and r1 to rt are called the multiplicities of f pi i's. So, what is the radical ideal corresponding to this? You just have to forget these powers. So, this is precisely ideal generated by the different primes, product of different primes. These are also called square free polynomials, where pi 1 to pi t are monic irreducible polynomials, monic irreducible polynomials in R x. So, we know radical ideals in terms of the generators, and where does it go? It goes to 0 set of this complex 0 set. Anyway, they do not have real zeros, so we have to look for the complex zeros. So, where do they go? Some of them may be linear also. The linear will correspond to the real 0 and non-linear will correspond to the complex conjugate zeros, because so then in any case pi 1 to pi t have finitely many complex zeros. Therefore, this product will have finitely many complex zeros, and therefore, this where will this set go? Under VL. So, VL of pi 1 to pi t is precisely union of VL of pi i's. I is from 1 to t, and each one of this is a finite set, finite. In fact, of cardinality less equal to the degree of pi i's, because any polynomial of degree d cannot have more than degree zeros. So, therefore, this is finite set, it is a finite union. So, altogether it is a finite set, but this red line what we have taken, that is infinite set. Therefore, this one cannot come from any polynomial, any radical ideal. Therefore, this map is surjective. This what do you call it, real, this is imaginary axis, this is y axis. I should actually not call y axis, let me just call it I axis. So, what we have checked is I axis, which is a subset here which belongs here, but which does not belong here, or for that matter any infinite subset, any infinite, there are lots of infinite subsets of complex numbers, they cannot be affine algebraic sets, and so therefore, this map cannot be surjective in general. So, we have to ignore outside this, you have to ignore this. So, now you can at least ask whether every affine, now it is by definition surjective, any affine algebraic set is coming from some radical ideal. So, we will continue this with more examples in the later half of this one, so that we can get acquainted with what is going on. Okay, thank you. We will continue after the break.